Good morning, everyone. Today we're starting a new and exciting chapter, Chapter 8, which is all about probability distributions. This is a core topic that builds on your previous knowledge of probability and statistics, and it allows us to model and understand situations involving uncertainty and chance. Over the next few lessons, we'll cover several key areas. We'll start by learning about discrete random variables and how to describe them using probability distributions. Then we'll learn how to calculate a very important measure called the expected value. Later in the chapter, we'll explore two of the most important probability distributions in all of statistics, the binomial distribution and the normal distribution. And we'll also see how to use our graphing calculators to make some of these calculations easier. So, we have a lot of powerful tools to learn that will help us make predictions and informed decisions in the face of randomness. To get our minds warmed up, let's start with a little activity. Look at the images on the screen. We see some extreme cases here. One of the world's tallest men next to one of the shortest, an athlete pushing the limits of human high jumping ability, and a person who has lived a very long life. Each of these images represents a variable: height, athletic performance, lifespan. Think about this question: how are these variables distributed in the general population? For example, if we were to create a histogram of the heights of all adult men, what would it look like? Most men are not as tall or as short as the men pictured. Their heights would be clustered around an average value, with very few people at the extreme ends. This is a key idea in probability distributions. Not all outcomes are equally likely. Now let's consider a different kind of problem. If you roll a fair six-sided die 10 times, what do you expect the mean score to be? Take a moment to think about that. You might get a mix of ones, twos, threes, and so on. But if you were to average those 10 results, what would you expect that average to be close to? This idea of an expected average is something we'll formalize today. It's a central concept called expected value. Before we dive into the new material, let's quickly review a couple of concepts you should be familiar with. This will help set the stage for what's to come. First, let's tackle a probability problem. Imagine a bag with 6 red and 4 blue balls. We draw 2 balls, one after the other, without putting the first one back. We want to find the probability of getting 2 red balls and the probability of getting exactly 1 red ball. For part A, the probability of the first ball being red is 6 out of 10. Since we don't replace it, there are now 5 red balls and 9 total balls left. So the probability of the second being red is 5 out of 9. To get the probability of both events happening, we multiply these probabilities together. 6/10 times 5/9 gives us 30 over 90, which simplifies to 1/3. So the probability of drawing 2 red balls is 1/3. Now for part B, getting exactly 1 red ball. This can happen in 2 ways. We could draw a red, then a blue, or a blue, then a red. We need to calculate the probability for both scenarios and add them up. The probability of red then blue is 6 over 10 times 4 over 9. The probability of blue then red is 4 over 10 times 6 over 9. Both of these are 24 over 90. Adding them together gives 48 over 90, which simplifies to 8 over 15. This type of calculation, where we consider different outcomes of a random process, is exactly what we'll be doing today. All right, let's get into the first main topic of the chapter, discrete random variables. That might sound complicated, but the idea is quite intuitive. It's simply a variable whose value is a numerical outcome of a random phenomenon. We usually denote a random variable with a capital letter, like x. The discrete part is important. It means the variable can only take on specific, separate values, which you can count. For example, the number of heads when you flip a coin 3 times can be 0, 1, 2, or 3. It can't be 2.5. That makes it discrete. A classic example is rolling a fair die. We can define a random variable, let's call it x, to be the score we get. The possible values for x are the integers from 1 to 6. Now, for any random variable, we can describe it using what's called a probability distribution. This is simply a list of all the possible outcomes for the variable, along with the probability of each of those outcomes occurring. For our die roll example, the probability of rolling any specific number, say a 2, is 1/6. We can write this using formal notation. We write P for probability, then in parentheses we put the event we're interested in. X equals 2 means the random variable x takes on the value 2. So Px equals 2 equals 1, 6. This notation is standard, so it's important to get comfortable with it. And here is the first and most fundamental key point. For any valid probability distribution, if you add up the probabilities of all the possible outcomes, the total must be exactly 1. This makes sense because one of the outcomes has to happen. The Greek letter sigma here just means sum up. This rule is incredibly useful as it allows us to check our work and even find missing probabilities, as we'll see in a moment. Let's apply these ideas to a concrete example. This is similar to our warm-up problem, but now we'll formalize it using the language of random variables. The problem is as follows. A drawer contains 5 black socks and 3 red socks. We randomly pull out 2 socks without replacement. Our goal is to find the probability distribution for the random variable x, where x represents the number of red socks we draw. First, let's think about the possible values for x. If we draw 2 socks, how many of them can be red? Well, we could draw 2 black socks, which means we get 0 red socks. We could get 1 of each, meaning 1 red sock, or we could be lucky and draw both red socks. So the possible values for x are 0, 1, and 2. To find the probabilities for each of these values, a tree diagram is an excellent tool. It helps us visualize all the possible sequences of draws and calculate their probabilities. Let's draw it out. We start with 8 socks in total, 5 black and 3 red. The probability of the first sock being black is 5/8 and red is 3/8. Now for the second draw. If the first was black, there are 7 socks left, 4 black and 3 red. So the probability of the second being black is 4/7 and red is 3/7. If the first was red, there are 7 socks left, 5 black and 2 red. So the probability of the second being black is 5/7 and red is 2/7. Now we can find the probability of each complete outcome by multiplying along the branches. The probability of getting 2 black socks, BB, is 5/8 times 4/7, which is 2056. Black then red, BR, is 1556. Red then black, RB, is also 1556, and 2 reds, RR, is 656. The final step is to link these outcomes to our random variable x. The event x equals 0 corresponds to the outcome BB, so its probability is 2056. The event x equals 1 corresponds to either BR or RB. Since these are mutually exclusive, we add their probabilities. 1556 plus 1556 gives 3056. The event x equals 2 corresponds to RR, with probability 656. We can now present our final answer as a probability distribution table. We list the values of x, which are 0, 1, and 2, and their corresponding probabilities after simplifying the fractions. So px equals 0 is 514, px equal 1 is 1528, and px equals 2 is 3/28. As a quick check, let's add these probabilities. 5/4 is 10/28, so we have 10/28 plus 15/28 plus 3/28. That's 28/28, which equals 1. Perfect, our distribution is correct. Now let's look at another example that shows how we can use that key property that all probabilities must sum to 1. Here we have a probability distribution for a random variable y, which represents the number of cracks found in a 1-kilometer region of sewer pipe. Notice that one of the probabilities is unknown, labeled k. Our first task is to find the value of k. How can we do this? We use the fact that the sum of all the probabilities in the table must equal 1. So we can set up an equation. 0.45 plus 0.3 plus 0.15 plus k must equal 1. Adding the known probabilities gives us 0.9. So 0.9 plus k equals 1. Solving for k, we find that k must be 0.1. It's that straightforward. Next, let's find the probability that y is less than or equal to 1. The statement y is less than or equal to 1 means that y can be either 0 or 1. These are mutually exclusive events, so we can simply add their probabilities. Looking at our table, py equals 0 is 0.45 and py equal 1 is 0.3. Adding them together, we get 0.75. So there's a 75% chance of finding 1 or fewer cracks. Finally, let's tackle a conditional probability problem. Find the probability that y equals 0, given that y is less than or equal to 1. Remember the formula for conditional probability. The probability of A given B is the probability of A and B divided by the probability of B. In our case, A is the event y equals 0 and B is the event y equal 1. The intersection y equals 0 and y1 is just y equals 0 because if y is 0, it's automatically less than or equal to 1. So our formula simplifies. This becomes the probability of y equals 0 divided by the probability of y1. We already calculated p of y1 to be 0.75, and we know p of y equals 0 is 0.45. So we have 0.45 divided by 0.75, which simplifies to 45 over 75, or 3/5, which is 0.6. This means that if we know there is at most one crack, there is a 60% chance that there are actually 0 cracks. Okay, let's move on to another central concept for random variables: the expected value. The expected value is, in essence, the long-run average outcome of a random experiment if you were to repeat it over and over again, infinitely many times. We denote it as E of x, or sometimes with the Greek letter mu, which you'll remember is also the symbol for the population mean. And that's no coincidence. The expected value is the theoretical mean of the random variable. Let's go back to our dice example. The outcomes are 1, 2, 3, 4, 5, 6. If you rolled the die thousands of times, you'd expect to get about the same number of 1s, 2s, 3s, and so on. The average of all those rolls would get very close to 3.5. So the expected value of a single roll of a fair die is 3.5. Notice something important here. The expected value does not have to be one of the possible outcomes. You can't roll a 3-5 on a standard die. It's a theoretical average. Also, don't confuse it with the mode. For a fair die, every outcome is equally likely, so there's no single most likely outcome. So how do we calculate it from a probability distribution? We use a formula that gives us a weighted average. The formula for the expected value E of x is the sum, that's the sigma, of each possible value x multiplied by its probability, P of x equal x. You take each outcome, weight it by how likely it is to occur, and then add them all up. This formula is one of the most important ones in this chapter, so make sure you understand it and commit it to memory. Let's practice using this formula with an example where the probability distribution is given by a function. We have a random variable y that can take the values 2, 3, or 4. The probability of each value is given by the formula P of y equals y is 0.125 times the quantity y squared minus 7y plus 14. Our task is to find the expected value of y. The first step is to figure out the actual probabilities for each value of y. We need to build our probability distribution table. So let's evaluate the formula for y equals 2, y equals 3, and y equals 4. When y is 2, we plug it in. 2 squared is 4, minus 7 times 2 is 14, plus 14. That's 4. So we have 0.125 times 4, which is 0.5. When y is 3, we get 9 minus 21 plus 14, which is 2. 0.125 times 2 is 0.25. And when y is 4, we get 16 minus 28 plus 14, which is also 2. So the probability is again 0.25. Let's put this into our table. Notice that the probabilities 0.5, 0.25, and 0.25 add up to 1, as they should. Now we have the distribution. We can apply the expected value formula. Remember, we multiply each value of y by its probability and sum the results. So E of y is 2 times 0.5 plus 3 times 0.25 plus 4 times 0.25. That's 1 plus 0.75 plus 1. Adding these up, we get 2.75. So the expected value of y is 2.75. One of the most common applications of expected value, especially in this course, is in analyzing games of chance to determine if they are fair. What do we mean by a fair game? In everyday language, fair can mean many things, but in mathematics and probability, it has a very precise definition. A game is considered mathematically fair if the expected gain for a player is exactly 0. This means that if you were to play the game over and over, you wouldn't expect to win or lose money in the long run. You'd expect to break even. The expected gain is calculated by taking the expected payout, which is the amount you expect to win back, and subtracting the cost you paid to play the game. Let's analyze a game to see if it meets this definition. Here's the scenario. Hiroki pays $4 to play. He rolls a standard die, and his payout is the number he rolls. For example, if he rolls a 5, he gets $5 back. Is this game fair? To answer this, we need to calculate Hiroki's expected gain. First, let's find his expected payout. Let's define the random variable x as the score on the die. The payout is equal to x, so the expected payout is just the expected value of x, E of x. We've discussed this before. What is the expected value of a single roll of a fair die? We calculate it by multiplying each outcome by its probability, which is 1/6 for all of them, and summing them up. This gives us 21 divided by 6, which is 3.5. So Hiroki's expected payout is $3.50. Now we can find the expected gain. We take the expected payout of $3.50 and subtract the cost to play, which was $4. This gives us a result of -50. Since the expected gain is not zero, the game is not fair. The negative value means the game is biased against Hiroki. On average, over many games, he can expect to lose 50 cents each time he plays. This is, of course, how casinos and lotteries make money. The expected gain for the player is always negative. All right, let's quickly recap what we've learned today before you get started on some practice problems. We've covered a lot of ground. We defined discrete random variables and their probability distributions. We established the crucial rule that probabilities must sum to 1. We then introduced the concept of expected value as a long-run average and learned the formula to calculate it. Finally, we applied this to the practical context of analyzing games of chance. These are foundational skills for this chapter. The best way to solidify them is through practice. Let's do one more quick example together from your exercises. Consider this probability distribution for a random variable y. Let's find its expected value. We just need to apply our formula, sum of y times p of y equals y. So we have 1 times 0.4 plus 2 times 0.1 plus 3 times 0.5. This gives us 0.4 plus 0.2 plus 1.5, which sums to 2.1. The expected value is 2.1. Excellent. Now, I'd like you all to work on the problems in exercise 8A. This will give you plenty of practice with creating distributions and calculating expected values. We'll discuss the answers later. Let me know if you have any questions.